like one really good problem, I think. There's a couple conceptual ones that are kind of interesting. So chapter 13 is all about solids and modern materials, meaning things that we use in our everyday lives, which maybe weren't here 100 years ago. The first section, of course, is just that interesting section. They're talking about graphene and how they discovered graphene. Graphene is one of the things that's in graphite. It's a single atom thick. So graphene's all carbon. So carbon is really interesting. That's why there's a whole year of OChem for it. There's so many different forms of pure carbon. There's diamond, there's coal, and then in the middle, there's all these really cool structures. And graphene is one. It's really flat. It's a single atom thick, super strong, conducts electricity really well. You'll see later in the chapter these really cool pictures of, they're called nanotubes. This carbon, it's kind of like graphene, which is a flat sheet, but wrapped up into a tube, a nanotube, and they're really small. Some of the people in my lab in grad school were doing some kind of crazy experiments with nanotubes. Again, they conduct electricity really well. Then the next section, 13.2, I'm not going to ask you any questions on these. They have these crazy questions on thickness of layers and diffraction angles, maximum reflection angle. I don't know how to do that stuff, so I've never seen it before, so I'm not going to ask you to do it. But they do explain this really cool experiment called X-ray crystallography. And this has been used for about 100 years. This is one of the key ways that we know the structure of chemicals. And you might remember back in Chem 1A, hopefully you heard a little bit about scanning tunnel microscopy. You put a little bit of a material down on a really flat surface and you use that needle with a single atom thick to scan over the top, and you look at the conducting properties and you get this picture of what the chemical was. So that's one way. That's a relatively easy way now to get the structure of some small materials. X-ray crystallography, though, is still way better, still really widely used. The trick on X-ray crystallography is that you first have to get a crystal, and this can be super challenging. 100 years ago, we were using X-ray crystallography for pure chemicals, metals, ionic compounds, maybe even some really small covalent compounds. And it was pretty easy to get a crystal. And then the first things they put in there would have crystallized easily. So you could have put like salt in there. You know, salt crystallizes, or sugar. Rock candy is a crystal of sugar. You could put that in there. So right there in the very middle, that's the key part. And it's actually a really hard thing to get now, because people are now putting much bigger molecules in there. So again, sugar has a molecular weight, something like 80, I think, 84. People are now putting molecules with molecular weights of 84,000. Those are proteins. Even 10 times bigger than that, 840,000. They're trying to get crystals of these proteins and sugars and little pieces of DNA. And how does a molecule bind to a protein? They're trying to get that complex, crystallize it, and get a little crystal to put in here. So sometimes the crystals are super microscopic. And I know quite a few people that spent years trying to get one type of crystal, and they would have to either make or purify a protein. Then they would set it up in all these different conditions. There's no like, if you're making the crystal for the very first time, you can't just like go to a chemistry cookbook and say like, oh, how do I get a crystal structure of lysozyme? You have to go figure it out. And we don't have like a great way to predict what's the best way to make a crystal of any particular protein. So you got to set up thousands of different conditions. You use these little trays, and they got a well, sometimes like 84 or 120 little wells in a little plate this big. And you put all these different conditions here. So like in one well, 1 molar salt, pH 7. The next one, 1 molar salt, pH 8. And then as you go down, maybe instead of 1 molar salt, maybe do 0.9 molar salt, pH 7. So you vary the conditions very subtly, and then you put your pure protein in there and you mix it up pretty good. And then you just put it in a dark shelf and let it sit for months at a time. And you get really impatient, and every couple of weeks you might peek in, and are there any crystals? And you get really excited about one, but then you look at it a little bit harder and you realize, oh, it's just the NaCl that's crystallized. It's just the salt. It's not your protein. And finally, after months and months of waiting and getting really mad and frustrated, one tray, you might get one crystal. But it's a really small little crystal because this was just a test. So then you try to reproduce those conditions, but on a bigger scale to get a bigger crystal. And most of the time it wouldn't work. It was kind of a fluke. You have no idea how you got that first crystal. But every once in a while, it was a real crystal, and those conditions, you can replicate it and you can make a new crystal. Now you got the crystal. You put it in this X-ray crystallography device. It's not a ton of people that have this instrument. It has to emit X-rays and then be able to figure out what's happening on the other side. So let's talk about it a little bit more, and I'll tell you about where they are. So you put your crystal in the middle. You got an X-ray source over here, which is ejecting X-rays. The purple here is the X-rays. So you got to have a lead screen, which will block most of the X-rays. So you got a very narrow beam of X-rays coming through, colliding with the crystal. And then your crystal is usually like on some sort of platform or held up so that you can kind of rotate it around a little. Because a lot of times the X-rays, as they go through the crystal, you just get that same beam. But you get just the right angle, and all of a sudden you get a really pretty picture like they're showing here. They're showing us the back because it would be hard to show everything. This is what you would see on the other side. This side would just be all black. But if you could see the other side, it's almost like a constellation. The X-rays have been blocked by some parts of the atom in the crystal, and they've been directed towards other places. So you got these individual atoms here, and maybe an X-ray can sneak through, maybe it gets blocked, and maybe it'll like kind of veer off, and so this one goes through and collides with it, and so you get a bright spot on the other side. That's all I really know about crystallography. There is a whole world of understanding in how you take that diffraction pattern, and turn it into a 3D structure. The little that I understand about it now is that people can just use computers, and you tell the computer which elements you think were in there, and it tries to fit the elements in a special pattern that would mimic or that would have given rise to this diffraction pattern. And then it makes all these little adjustments until the predicted and the experimental pattern match, and now you've got your crystal structure. It turns out that there's only a couple places that have really good X-ray crystallography instruments. And one of the biggest and best, at least on the West Coast, is in Berkeley. So I knew a lot of people in grad school where they would finally get their crystal after years and years of hard work. And they would call up Berkeley and they'd say, oh, we need to use your X-ray crystallography instrument. Can we please borrow some time? I think they paid for it anyway, and be like, well, let's check the schedule. Like, okay, so Thanksgiving weekend on Thursday from midnight till 8 in the morning, it's open. It's yours if you want it. And you say, oh, thank you, please, we'll take it. We'll be there. You drive up the coast with your crystal, and you get there at midnight, and you spend all night trying to move the crystal in just the right way to get this pattern. You get the best pattern you can, 8 in the morning. You get out of there because the next person is ready to come in, and hopefully you got the right data. You take it back to your lab, and hopefully that it all works out and makes sense, and you got the data to publish a paper. Is anybody signing up to do some X-ray crystallography? You actually might, when you get to grad school, you might end up doing this stuff. So again, kind of an interesting idea in there. They try to give a problem on diffraction patterns and angles, but I don't want to do that. This is the big chapter that I wanted to talk about, chapter 13, unit cells and basic structures. Yeah, it would be a part of material science. Okay, so you got your structure in hand. People were doing this for all sorts of chemicals. 100 years ago, it would have been really exciting to do this with atoms. You might have heard, I always forget her name, and I always should remember it for today. I think I did that. DNA crystal structure. Okay, so this was happening in England. There's these two scientists, which you've probably heard about, James Watson and Francis Crick. They were big scientists at one of those fancy schools in London. And then she's kind of like a tech, although she ended up going to be a professor, I think, at a different school. Her name was Rosalind Franklin, and she was a really good lab scientist. She could get really good data. She had just, one of those pairs of hands that you really wanted to be on your team. And she was working in a different lab with somebody else, and she was working on the structure of DNA. And Watson and Crick were also thinking about DNA, but they were kind of just approaching it, from what I can tell from what I remember, from like a theoretical perspective, like, oh, here's the chemicals, how do they stick together? They were trying to build models and stuff like that. Maybe they were trying to get the crystal structure, I don't know. But Rosalind Franklin, she crystallized a little piece of DNA, and she got a good crystal structure. She got a really good diffraction pattern. It's got this kind of classic X pattern to it. And then she kind of set it aside. She had a lot of different things on her plate. And so this wasn't really the top priority, although it was one of the big priorities. And so she kind of is really fuzzy at this point because she died pretty young. It looks like she was 38 years old when she passed away. And so we're not really sure what happened. Next thing you know, Watson and Crick, one of them had seen this crystal structure, the diffraction pattern. Maybe they took it. Maybe they were prying where they shouldn't have. Maybe Rosalind Franklin had left it open and they just walked by and saw it. That's the way that they will make it sound. Kind of fuzzy from their perspective. But they recognize what the pattern means. Like, oh man, this means something. This means the DNA is in that, what you've seen now probably, the double helix. So Watson and Crick get a lot of credit for it. They got the Nobel Prize for it, and Rosalind Franklin didn't. And before you get really, really mad, Nobel Prizes are only awarded to living people. And so Rosalind Franklin had died 4 years before they gave this Nobel Prize to people. She undoubtedly would have been one of the people that would have got the Nobel Prize had she still been alive at that time. But for a long time, decades, people wrote in textbooks, oh, Watson and Crick discovered the structure of DNA. And they may have done the very last step, the interpretation from the DNA, from the crystal structure diffraction pattern to the actual crystal structure. But that's not to say that Rosalind Franklin couldn't have done it. She probably would have. They kind of jumped the gun. They took her data and published it without her. So, yeah, go ahead and be really mad. But she would have got the Nobel Prize had she still been alive at that time. I can't remember how I got on that, but just kind of the most famous story about crystal structures. So a long time ago, you would have been studying elements and ionic compounds. In the 50s, you would have been studying DNA. And all the way up till now, you could be studying large proteins. I think they're even trying to do big complexes, maybe even trying to understand how organelles are formed at this point in time. And what you find with pure elements in a crystal is that there's this repeating pattern. And so here we got a two-dimensional repeating pattern. We got a bunch of circles. You can imagine them being atoms, maybe like gold or something like that. A really flat layer of gold in this repeating pattern. And the diffraction pattern is, on the one hand, it's telling you the whole big pattern, but on the other hand, you want to kind of zoom in on the smallest space that's repeating in all dimensions. And that's called the unit cell. And so that's what we have outlined in pink here. So the light pink you might recognize as also repeating. If you were to take this big square here, copy it, paste it over here, you could start to predict what the crystals would look like over here. But it's not the smallest yet, so we shouldn't call it this the unit cell. You go one smaller and you start to cut fractions of atoms. So right through there, if you take that pattern and repeat it in any direction, you get the same thing over and over and over again. And so again, this is just a two-dimensional one. So it's kind of interesting. This unit cell is the thing that gives rise to the overall crystal. The overall crystal has hundreds of billions of individual components, all perfectly kind of locked into this repeating pattern. But it started somewhere. It started with that crystal, that unit cell, the lowest energy. So crystal structures are starting from a lowest energy arrangement. So maybe these 5 atoms got together and they got as close as they possibly could. That was your smallest little crystal structure. And then every single other atom that came in locked into place to repeat that pattern in all directions, so that eventually you got this big crystal. I don't think I have any big, cool crystals in my office. Well, that's some rocks. I got really excited at like a book fair a couple semesters ago. I was like, years ago now, I guess. There's these minerals in these kits, and they're pretty cheap. I was like, oh, maybe we could do something like this with Intro to Chem. This one's pretty cool, I guess. Kind of just looks like a piece of salt or sugar, rock candy. This is calcite. I don't know anything about minerals. It's kind of weird to me how the geologists and chemists, they're just like, we'll talk about the same stuff, but we'll talk about it in such complete different ways that geologists and chemists won't have any idea what each other are talking about. So we go to Wikipedia and we look up calcite. You can follow along with me if you want. Go to Wikipedia, look up calcite, C-A-L-C-I-T-E. It's calcium carbonate. Oh, look, and then the box on the right, actually, maybe I should just share my screen with you. Okay, so I typed in calcite in Wikipedia. So this chemical right here is calcium carbonate, CaCO3. A lot of the stuff over here, you might well, never mind. As soon as you type it in, it's so weird, watch this. So look, calcite is something that you can find in the ground, and it's just calcium carbonate. But if you type in or click on calcium carbonate, you come over here and you have the chemist version, and it's in a powder. It's not in a crystal anymore. And you see all the things that we've been talking about all year: the molar mass, the density, the melting point, solubility in water, solubility product, KSP, the pKa, because carbonate is weak base. Okay, so here's some of the other things. Crystal structure. Is trigonal on here? Not exactly. Okay, let's go back to calcite. And look down here, crystal system, trigonal. And look, got a couple different crystal structures here. This one, look at that crystal structure. Each of those points would be where one of the atoms are, is a calcium or a carbonate. And it looks the same as the bulk crystal. So the individual unit cell gives rise to the overall shape of the crystal. Most of these are just some sort of silicon version. I got really excited and then I looked them all up and they were all silicates and they all had very similar densities, so I couldn't really use them. So now I got all these minerals just floating around up there. Oh no. Not rock candy. Could you guys see what I was showing you on Wikipedia or no? Please say yes. Ah, okay, well, can you see it now? Okay. So here is the mineral version, and they're talking about all these things over here. Here's the unit cell stuff, which is actually kind of what we're about to talk about. And then if you type on the chemical formula, calcium carbonate, you go to the chemist version, which has all the things that we've been talking about: molar mass, density, melting point, boiling point, solubility, KSP, pKa, because carbonate's a weak base. But over here on the crystal system, they're talking about unit cells. We'll talk about that in a second. And then the crystal system, it says it's trigonal. And so here's that rhombohedral. Got these edge lengths and these angles, and one of the angles isn't 90, which gives it that, it's kind of offset shape. I don't know if you can tell. So since it is soluble, I guess you could like eat it. It would be sort of like an antacid if you got any of it into your stomach, but it'd also be kind of basic. Okay. So anyway, minerals are pretty cool. They are just chemicals. Here are all the different types of unit cells. We're going to talk a lot about cubic. Cubic, all of the edges are the same and all of the angles are 90. So they're perfect cubes. All of these other ones, you see that tetragonal means one of the edges is a little bit longer. Orthorhombic means all of the edges are different. A and B and C, the three different edge lengths that you might have, are all different. But the top row has all 90 degrees. So they're all squares on each side, or rectangles on each side. And then the bottom row has angles that are different. And then sometimes angles and edge lengths could be different. I think we're only going to talk a little bit about hexagonal, a lot about cubic, and we don't talk about any of the rest of them. You could go and learn a lot about them and which chemicals adopt those, but we just don't have time. If you were in an upper division inorganic course, you might spend weeks talking about all these different structures. Here are the 3 cubic unit cells that we're going to talk about. They have different names based on how the atoms sort of overlap and how they stack and how many atoms are in the unit cell total. So the first one, pretty easy to understand, is called a simple cubic unit cell. I'm going to show you something over here called Z diagrams. This isn't in your textbook. I was teaching at a different school, and they made a big deal about these Z diagrams, and it's a lot better way to think about these and to try to show what's happening with 2 dimensions, because these are all 3-dimensional shapes. But when you're talking about atoms in front of atoms, some atoms always get hidden and they're hard to see, and Z diagrams really space it out. And so simple cubic, you see, is just a cube where there's 1 atom on every corner. So the atoms are stacked directly on top of each other. You got 4 atoms on top, 4 atoms on bottom, and you stack them directly on top of each other. If you went into a grocery store and you saw oranges stacked directly on top of each other like this, you would think that you were dreaming, right? It doesn't make sense. Only a psychopath would try to stack oranges that way, because they're going to start rolling all over the place. It's really unstable way to have atoms. Z diagrams, what we do is we take a sliver through the nucleus of every atom. We kind of cut, and we start at the bottom and we work our way up. And so here you would do a cut through the bottom, and you get those 4, and then you do a cut through the top. We call the bottom 0, we call the top 1. If we did another cut through the middle, we would call that 0.5. And so the Z diagram, you would have, when Z equals 0, you'd have 4 atoms, 1 on each of the corners. And then the top sliver, that Z equals 1, has an atom on all of the corners. So 8 atoms within the unit cell. And we're going to talk about these different things here in this table. How many total atoms are within the unit cell, coordination number, edge length, and packing efficiency. So first, atoms per cell. So with simple cubic, we saw only atoms on the corner. If an atom is on the corner, then each atom is 1/8 within the unit cell. So which one's easiest to see? Maybe this front one here on the left. Only 1/8 of it is within the unit cell, because another 1/8 would be in the neighboring unit cell like this. Another 1/8 would be in the unit cell in the front. Another 1/8 would be in the unit cell here in the front. And so that's 4 unit cells. And then you got to do the same thing on top. So you do 4 unit cells on the top. And that is a hideous picture, but hopefully as you watched it come into focus, you saw that that 1 atom was within 8 different unit cells, and therefore there's only 1/8 of the atom within that 1 unit cell. So an atom on the corner is 1/8 within unit cell, but there are 8 corners. 1 atom within unit cell. I think you can see it a little bit easier here with this professional diagram. If you look at this 1 atom in the very middle, it's in this front unit cell, but again, only 8. And then 2, 3, 4 in the back, and then on the top, 4 more, 5, 6, 7, 8. So that 1 unit cell is within 8 different, that 1 atom on each corner is within 8 different unit cells. Corners are sort of the trickiest to see. The rest of them get a lot easier. If an atom is on an edge of a unit cell, it's 1/4 within that unit cell. It's within 4 different unit cells. So 1/4 within unit cell. But how many edges are there within within 1 cubic unit cell? So you got 4 along the top, 4 along the middle, and 4 along the bottom. So there's 12 edges on a cube. So there's 3 atoms within the cube, within unit cell. So if you have atoms on an edge and it's on all 12 edges, then you'd have 3 total atoms. An atom on the face, this one's really easy. Half of the atom is within the unit cell. So you have your unit cell here, and you got 1 atom right on the face. I'm going to try and show it on the bottom face. Then half the atom is inside that unit cell. The other half the atom would be in the bottom unit cell. And how many faces do you have on a cube? 6 times 6 faces. So you have 3 atoms within a unit cell when you're talking about faces. And then the middle is the easiest. If you have an atom right in the middle of the unit cell, the whole atom is within the unit cell. 1 atom within the unit cell. And for us right now, there's really only 1 middle. But you will see with ionic crystal structures, you could have a bunch of atoms or ions all stuck in the middle. So you got 1 atom within the unit cell. Okay, so we talked a lot about simple cubic. Here it is again. Atoms are stacked directly on top of each other. Nothing in the middle. 4 on the bottom, 4 on the top. Let's talk about coordination number. This is how many other atoms every atom is interacting with or maybe bonded to. In the simple cubic unit cell, it's actually kind of hard to see because when you look at just 1 atom, so say we were looking at this one in the back, no, back's not a good one to do. In this front right here, it's only interacting with 3 other atoms in the same unit cell, to the right, above, and then the one in the back. So let me erase this and highlight it some way. Looking at that one in the front, it's interacting with 3 more in the same unit cell, above, to the right, and behind. But it's also interacting with atoms in neighboring unit cells, 3 other ones. It would be interacting with 1 to the left, 1 in front, and 1 below. So an atom on a corner in a unit cell is interacting with 6 other atoms, so we say that it's got a coordination number of 6. What about edge length? Edge length in terms of R. And I wrote here, it's a real application of geometry. So I think that's kind of cool on the one hand. On the other hand, I'm not going to ask you to like derive what these edge lengths are. I actually usually give this table on the front page of the exam or the final. It's part of the given information. So you just have to know where to go look and find this stuff. But we should also know where it comes from. And I didn't include the figures here for edge length, but if you want to know what it's easiest to see with this one. If you want to know what this edge distance is here, remember the nucleus is right in the middle. And from the nucleus to, since it's spherical, to the outside is the radius. And look, right along the edge, you got a radius from one atom and a radius from another, and they're touching right there in the middle. So an edge is equal to 2 radius. We're not going to be able to do that with the other ones because there's some gaps. They're not touching. So you got to do some fancy geometry to get the edge in terms of the radius. Look here, you got this big gap. But on the diagonal here, you got a radius, a radius, a radius, and a radius. And then you could do some Pythagorean theorem here, and you say, oh, the hypotenuse is 4 radius. What is it? A squared plus b squared equals c squared. And then you can say, well, c squared is 4 radius. And then you can, and then you say, oh, this is, what is it called? A right triangle. And so a and b are the same. And so you say, oh, 2a squared is 4r. And then a squared is 2r. And then a is, oh, it's not exactly right, but it's kind of close. I think you kind of see where we're going. The edge on that last one is 2 times root 2r. I didn't do it quite right. I'm not sure where that last 2 came from. But again, you kind of see the thinking here. You're finding the radius, where they touch, and you kind of put that in perspective of the edge. We want to know what the edge is because we're going to need to know what the volume of a unit cell is. So edge length, the real application of geometry. This is the length of one edge in terms of the radius. And so simple cubic is 2r. Face-centered cubic I tried to do, got hung up somewhere along the way. Your book does go in depth on all of this stuff. But again, I don't test people on how did you get this edge length, because I just give you that table and so you can go and look them up. Oh, I forgot to square. That's why. Right here. I forgot to square this. Anyway, so that means this is wrong, but this is right. Okay. And then you should also remember that the volume of a cube is based on the edge cubed, right? These are all those perfect unit cells, those perfect cubes where every, the length, the width, and the height are all the same. And so the volume is equal to one edge times another edge times another edge. So the edge cubed, we're going to use that here in a second. And then finally, packing efficiency is the volume of atoms within the unit cell divided by the entire unit cell, the volume of the unit cell, times 100. This is telling you how much space is occupied by the atoms. Remember, atoms are mostly electron clouds. So how much space is occupied by electron clouds? Because some of the space, and I think, again, it's easiest to see with this simple cubic, a good chunk of the space is just empty space because of the way the atoms are stacked. And so for a simple cubic unit cell, look, we got just one atom within the unit cell. And so for simple cubic, what is the volume of the atom? So the volume of a sphere, this was the volume of a cube. The volume of a sphere is 4/3 pi r cubed. And so volume of the atoms within the unit cell. We already said that simple cubic has only one atom within the unit cell. It's a fraction of 8 different atoms. But so we got 4/3 pi r cubed. I'm going to do a times 1 right here because it's multiplied by however many atoms are within the unit cell. And then divided by the volume of the unit cell. And look, we said that the edge of a simple cubic was 2r. So we could do 2r is the edge cubed. And then this has to get multiplied by 100 to get your packing efficiency. Two cubed is 8. So we're looking at 4/3 over 8 pi r cubed times 1 over r cubed. You see, it's kind of interesting. It doesn't even matter what type of atom it is. R cubes go away. And then that 4 and 8 can't simplify down to 1/2. So now we got, it's like pi over 6, which I think is right. 3 times 2. And so if you take pi and divide by 6, 52.36. Please tell me I think that's right. Okay. Four over 24, the same as 1/6. Okay, good. 50, and then times 100. I keep forgetting that, times 100. 52.4%. So a little over half the space is atoms, which means a little under half the space is empty space. And you see that simple cubic has the lowest packing efficiency. There aren't too many materials that pack in simple cubic. I think polonium might be the only one really, but on the other hand, it's sort of the easiest to see. So we're going to go through these other two a little bit more quickly. I'm not going to try to prove packing efficiency. In body-centered cubic, you've got, let's go through them down here. It's a little bit easier. So on the far right, you have the unit cell. They're showing them in different colors, even though we're still talking about pure materials. So each of these atoms is the same atom, but they're just showing different positions. So that middle gold one is the same as all 8 of the purple. But you got one atom in the middle, that's one atom. You got 8 corners, and an 8 times an 8 is 1, 1 plus 1, 2 atoms within the unit cell. The coordination number, this one's actually a lot easier to see because you got the middle atom here, and look, it's connected, it's interacting with all 8 corners. So its coordination number is 8. Its packing efficiency, you would do the same thing. You take the volume of the atoms within the unit cell, but that's multiplied by 2, divided by the volume of the unit cell. But notice that the edge isn't 2r anymore. Again, we kind of talked about that over here. This one's really tricky to see because it's from one corner to the exact opposite corner. So if you start up here and you draw a line from the back top right to the front bottom left, that is 4 radius. So you got to draw a really fancy triangle to get this edge. And then this one, I don't even know what that is. But anyway, that super diagonal through the middle is 4 radius. And you can do some really cool geometry. It's in the textbook to get that edge. And it pops out to what it says up in the table, 4r over root 3. A lot more elements will crystallize in this structure because this is 68%. It has 68% packing efficiency. So it's a lot more stable. And then the last one that we'll talk about is face-centered cubic. Get rid of my bad algebra here. Face-centered cubic, so the name kind of represents the structure. And here you got your 8 corners. So that part's the same. But now you've got 6 more atoms, and instead of being in the middle on body-centered, you have them on the faces. And remember, an atom on the face is half within the unit cell. So 6 faces times a half. There are now 3 plus 1, 4 total atoms within the unit cell. This one's really hard to see with coordination number. Got to look at faces. They're looking at this one atom here, which is on the face in that back blue unit cell. So this one right here. It's interacting with 4 on the corners. Those are easy to see. It's also interacting with the 4 on the faces behind it. 5, so I'm doing the yellow ones behind. And that means it's also interacting with 4 on the faces in front of it. And they're not even showing all of those, but it would be 9, 10. There would be another one here, which would be 11, and another one above, which would be 12. And so that's why the coordination number is 12. And again, packing efficiency would now be the volume of the atoms. So one atom is 4/3 pi r cubed, but now there's 4 atoms within the unit cell over the volume of the unit cell. If you go to the table, you see that an edge in face-centered cubic is 2 times root 2r. So that's one edge, and then you cube this. And if you simplify this down, again, I'm not going to ask you to prove packing efficiency, but it comes out to 74%. This is as close as pure atoms can get. This is minimizing the space, getting the atoms as close to each other as possible. With Z-diagrams, we try to show this 3-dimensional structure by, again, taking cuts. You would take a cut through the bottom, through the middle, and the top. And so you would have Z equals 0 and 1 and a half. On the bottom, you've got your 4 purple atoms on the corners. In the middle, you have your middle atom. And on the top, you also have those 4 cuts, 4 atoms on the corners. I think it could be a lot easier if you practice a little bit of Z-diagrams to count the atoms within the unit cell. So you realize that if you're talking 0 or 1, you're talking corners. Actually, let me put some letters in here instead. So we'll do corner. All of these are corners. This is a middle. And just for reference, if you were talking like something in the middle and you were talking here, those are faces. And if you had a cut that was in the middle of the unit cell, or sorry, let me, on the top or the bottom, sometimes you'll see either 0 or 1. It's both of them. So you see, usually the top cut and the bottom cut are the same. If you see an atom on one of those sides, those are edges. And again, those are a quarter. So let's look at the Z-diagrams for face-centered cubic. Again, you got 3 cuts that we need to make. Through the bottom, through the middle, through the top. So we got 3 cuts, 0, half, 1. These are all cubic, so they're all squares. 0 and 1 had an atom on all of the corners, but look, they also had an atom in the middle. If you're talking about the top or the bottom, those are faces, and the rest are corners. And then half, so I'm looking here on the 0 half, I see the 4 on the faces in the middle. So each of those are a face. So now you can see, oh, I got 6 faces, 8 corners, 4 total atoms for that packing efficiency. Your book will talk a little bit about closest packing structures. They show one more non-cubic unit cell is hexagonal closest packing. That's the name of it. And it's not cube, it's now, I guess, a hexagon. And the bottom layer and the top layer are the same. And then the middle layer is sort of offset. So that's why they're different colors like that. And I don't know if they talk about packing efficiency on this one. They should. It might also be just 74%. I think it is 74%. It turns out that cubic closest packing, so if you look at them in terms of atoms stacked on top of each other, you now got 3 atoms. This is the way that you would set up oranges if you worked at a grocery store. You got the bottom, and you would range 3 atoms on top of that bottom one. So 1, 2, 3, kind of offset. And then the row above it would have 3 more atoms, but twisted, like 60 degrees or something. And so now those 3 atoms that I've put dots on in red are now surrounded by the 6 blue atoms, so third, and then you repeat. And it's really hard to see, but you take my word for it, take the book's word for it, that when you put these together and then turn it on its side, you get back to face-centered cubic. And here's that green, here's that other green. So you got the 3 layers, and then you repeats, and it turns out that this is face-centered cubic with the 74%. Okay, so those are the simple cubic unit cells. Again, we could have spent weeks and weeks and weeks talking about these other unit cells. We've only talked about cubic. We showed a hexagonal one, which is here, I guess, although it doesn't really look like it. And I think you can see now why we talk about unit cells in 2D first. These are the 3 cubic unit cells that we see most of the elements on the periodic table adopt. Body-centered and face-centered cubic are way more prevalent because they're way more stable. Talked about atoms in a cell, counting corners, edges, faces, and middles. We talked about coordination number. We talked about edge length a little bit. You know, again, I'm not going to ask you to prove that stuff, but hopefully you got a picture of where it's coming from. People are doing some cool geometry. And then we talked about packing efficiency. There's a lot of simplification here, but it's the volume of the atoms on the top divided by the volume of the unit cell, so the edge cubed times 100. And now we get to the really cool problem from this section, relating the density of the unit cell to the density of the macroscopic material. So if you remember back to Chem 1A, one of the first equations that you had was density. Density is equal to the mass divided by the volume. This was one of the first ways that people had to figure out if a chemical was gold or fool's gold. It was one of the first ways we had to identify a chemical because it's pretty easy to measure. You measure the mass, you measure the volume, mass divided by the volume. Usually mass is in grams, volume is in milliliters, which is the same as centimeters cubed. And every chemical has a unique density. It's a constant. Gold always has a density of 19. Water always has a density of 1. Aluminum is like 2.7, I think. So pure chemicals have consistent densities. It doesn't matter if you have a little, big amount, or a huge chunk. The density will be one number. And it turns out, the way that they always show these problems is kind of like this, is where we're going to go find density. But the way that it really turns out was used was we knew the densities of all these different elements. We knew what the density of chromium was. Once we got the crystal structure and we saw that it was body-centered, now all of a sudden we could find the radius. But let's buy into this question the way it is. Chromium crystallizes with a body-centered cubic unit cell. The radius of a chromium atom is 125 picometers. Calculate the density of solid crystalline chromium. So again, this is kind of mind-blowing, I think. We're finding the density of the smallest chunk of crystal. and it's going to apply to the macroscopic object. It's kind of cool. We're going to use density. We've got this radius, 125 picometers. We see that the volume is going to be in centimeters cubed. It probably makes a lot of sense to convert this into centimeters. So get out of picometers into meters, get out of meters into centimeters. A pico represents 10 to the minus 12. And so 125 divided by 1 times 10 to the 10th, because it cancels with 100 and 1 times 10 to the 12th. And you get 1.25 times 10 to the 8th minus 8 centimeters. So that's the radius of an atom in a body-centered unit cell. From radius, we can go find the edge. Again, we're going to use this information here in a couple different ways. You go to the table on page 546. Body-centered has an edge 4r over root 3. So let's find the edge. 4 times the radius, 0.25 times 10 to the minus 8, over the square root of 3. This is 1.732. So you take 1.25 times 10 to the 8, divide by the square root of 3, times 4. Now we got the edge is 2.887 times 10 to the minus 8 centimeters. Now we need to know the volume of the unit cell, and we know that these are all cubic, so volume is equal to edge cubed, so it's 2.887 times 10 to the minus 8 centimeters cubed. So you take your number on your calculator, raise it to the third power, and you get 2.406 times 10 to the minus 23rd centimeters cubed. So now I got the volume of the unit cell, but now I need to know the mass. We know that chromium, if you look it up on the periodic table, is 52 grams per mole, but that's for a whole mole. In unit cells, we're talking about individual atoms, either 1, 2, or 4, depending on how it crystallizes. So get out of moles into Avogadro's number. This tells you how many grams 1 chromium is. So 52 divided by Avogadro's number, 8.635 times 10 to the minus 23rd grams. But this is body-centered, and body-centered has 2 atoms. So this is grams per atom times 2 atoms, 1.727 times 10 to the minus 22 grams. And now we got the 2 units we need to find the density. Density is mass divided by volume. The mass is 1.727 times 10 to the minus 22 grams divided by the volume, 2.406 times 10 to the minus 23rd centimeters cubed. So take your number that you got here in mass, divide by 2.406 times 10 to the 23rd, 7.18 grams per centimeter cubed. Take this problem from. I don't remember where I took this from. Might be, is it the blue box at the back? No, that wouldn't make sense. That would be a multiple choice problem. Well, anyway, we could go look up the density for chromium. I got a periodic table here somewhere. Density right there in the middle, 7.14. So that's pretty cool. Find the density of a unit cell And it's the same as the whole macroscopic material. And again, I kind of said it at the beginning, it probably didn't mean too much, but the way that this information would really be used is we've known densities for a really long time. So they're pretending like we don't know it, but we would know this. And once you do X-ray crystallography, now you know how it crystallizes. Those two pieces of information, you can work backwards to find the radius. This is one of the ways that we get the radius for all the different elements. X-ray crystallography plus density. Doing this problem sort of backwards. There's some good problems in the back of the book in chapter 13 that walk you through this process a couple different times. Okay. So then there's some sections in the middle here, which again, they just got some interesting information, kind of trying to take the realm of possibilities and just kind of combining it into a small, like, this is the way we find nature. And so one of those is, how do we find solids? And so if you take all the different chemicals that we know about, atomic, ionic, molecular, and you crystallize them, try and lump them into categories based on melting point. So you got a couple different crystalline solids. You've got molecular, ionic, and atomic. Molecular solids usually have very low melting points, on the order of room temp or lower. Even water has a really low melting point, 0 Celsius, so H2O, even though it's really polar. So molecular, again, those are 2 or more nonmetals. These are covalent compounds. They're only held together with intermolecular forces. And then ionic compounds, this is when you got full cations and anions, like NaCl. Those are held together with full charges, and they have really high melting points. I think table salt has a melting point in the thousands of degrees Celsius. And then the third category that we're talking about here is atomic solids. So this is one pure element. And here we should have 3 categories. So even though atomic is one of the 3 types of crystalline solids, atomic, there are 3 categories of atomic. You got non-bonding atomic solids. They always show noble gases here because they're not stuck together at all. They're just held together by those dispersion forces. They have really low melting points too, really low, like 40 Kelvin, stuff like that. Then you have your metallic atomic solids. These are all the metals. Most of the periodic table are metals. They have variable melting points. Mercury has a really low melting point. Gold has somewhere in the middle. And then some of the other metals have really high melting points. I think if I go back to this EMD app, this is kind of a cool app. Oops. It's called EMDPE, I think. So over here, EMDPTE. It's a free periodic table. And if I come over here, we go state of aggregation. We're at really low temperature. So I'm dialing up on the left over there. You can see green is solid, blue is liquid, light blue is gas, and gray is no data. We don't know what state of matter a lot of these radioactive materials are. If I slowly start to increase the temperature over here, we'll see helium is the first thing, and it's really hard to even find it solid. And then a little bit higher is helium. And as soon as they go from solid to liquid, they also go to gas. And then neon, you see the noble gases popping in, and then you see those diatomic covalent compounds, N2O2F2, more noble gases. Chlorine's now a liquid at -12 Fahrenheit. Now mercury. So mercury is a weird metal, right? It's melting down where covalent compounds and noble gases are. Bromine. This is around room temperature. A little higher than room temperature there. 46 Fahrenheit is kind of a cold room, cold outside. But mercury and bromine are the only elements that are a liquid at room temperature. And you see most of those non-metals are gases. And we keep going. Now we're starting to melt some of these other metals. And now we're starting, oh, look, mercury is the first metal that turns into a gas, 783 Fahrenheit. Keep going. Look, a lot of those metals, especially the transition metals, they're holding on tight. They're still solids at 2000 Fahrenheit. But now copper, silver, look, copper, silver, and gold are kind of weird. They're liquids at relatively low temperature. So you really worked really hard and cranked them up on like an outside coals or something. You could start to melt copper, silver, and gold, start to make your own jewelry, stuff like that. Look, carbon is really weird non-metal because diamond, which we're about to talk about, is super stable. It's held together by covalent bonds. So it's a solid even though we're at 3000 Fahrenheit. Keep going up. We're finding carbon and tantalum, tungsten, rhenium, and osmium are the last holdouts for the solid phase. And now, oh, diamond is the last one. We're at 6000 Fahrenheit. Diamond and tungsten, carbon and tungsten are the last solids. A little bit higher. Stop responding. Cool. Anyway, oh, it's just slow. There we go. There. Carbon's the last one. Some of the metals are liquids. Now carbon's melted in the liquid phase. And but look, it's kind of interesting. Tungsten is still a liquid here at 9,800 Fahrenheit. It was the last one, tungsten. 10,000 Fahrenheit to get it to boil into the gas phase. Oops. So atomic solids have extremely variable melting points. And we saw metals had variable and network covalent. This is going to be carbon. They're also showing, that's so weird that they put this down here under atomic. That doesn't make sense. This is under, I don't know where you'd put it. It's kind of its own category over here. Because again, it's two elements. So it absolutely shouldn't be under an atomic solid. Carbon, diamond is the classic one, which I think I got a picture of right here. Diamond is tetrahedral carbon, all sp3 hybridized. So one carbon is attached to 4 neighboring carbons with covalent bonds. And then each of those carbons is also attached to 4 neighboring carbons with covalent bonds. And so in effect, one diamond crystal is one molecule. This carbon atom on one edge of the diamond is attached by covalent bonds, single bonds, all the way to the other side to every other carbon atom in the diamond. And so it's one molecule. So that's kind of cool. And that's why it's so hard to melt. You don't really melt it. You eventually just start breaking those bonds. Graphite is also a covalent solid, but it's flat sheets held together with covalent bonds. And so it's really easy to shear it off one layer at a time. And that's why we can use it as pencil lead.